Hello, we are Team 7 and our project topic is Proximal Policy Optimization Algorithms. I'm Jungmin Park and I'll start the presentation. Before we dive into our main topic, we should know about the reinforcement learning. Here is a diagram of the system of reinforcement learning. We have two components, agent and environment. An environment has a state st. An agent makes an action at according to the probability pi zeta at given st. The action affects the environment and state is updated to st plus 1. A reward rt for making an action at is forwarded to the agent and the agent feedbacks according to the reward. Those state and action are naturally chosen by the given problem. For example, if we have a reinforcement learning system of autonomous car, action will be acceleration, handling, or extra, and environment will be its velocity, displacement, placement, or extra. So we have choice of implementations on how the agent chooses the action and how to give a feedback to the agent. We use a deep neural network parameterized by zeta for the action policy and give feedback to the agent by gradient method. To use a gradient method, we need a loss function. From now on, we are going to talk about various reinforcement learning algorithms that emerge according to various loss functions. Policy gradient method uses one of the most straightforward choice of the loss function. Since it can be too technical, I will just explain the high-level ideas of what those equations are. When you simulate a system, you will have a tau, which is a sequence of state st and at. For each time step, we can calculate an advantage at hat, and by summing all the at hat, we can measure how well simulated system behave. The average value of that value for every simulation is say zeta. Since the agent does better when this j zeta gets large, we do the gradient ascent to update zeta in the direction of improving j zeta. However, policy gradient method has poor performance due to some problems. First, when the policy changes a lot, it might destroy the whole learning. Second, improper learning rate leads to vanishing or exploding gradient. To overcome the problems of policy gradient method, trust region policy optimization updates zeta by this process. The expectation given here is an unbiased estimator of the loss function that was given in policy gradient method. Instead of updating zeta by gradient ascent, TRPO tries to simulate local search, neighborhood being the delta radius neighborhood of the old policy calculated by KL divergence. For those who don't know what KL divergence is, KL divergence measures how close two distributions are, and two distributions are close when KL divergence is small. However, when you use this kind of hard constraint, the problem gets really difficult when the policy network pi zeta is complex. We can convert the hard constraint problem to approximating soft constraint problem like this, which is similar to when we use L2 loss as a regularizer for reducing L2 norm for neural network. Now we solve the problem of policy gradient method, which was that large policy update might destroy learning process. However, we have another problem of choosing this proper beta value for TRPO algorithm. Finally, we can talk about the paper's main topic, proximal policy optimization algorithms. The paper suggests two proximal policy optimization algorithms, CLIP surrogate objective and adaptive KL penalty coefficient. Clip surrogate objective defines this RT, which is probability ratio between due and owed policy. This RT gets closer to 1 as the zeta gets close to zeta owed and becomes 1 when zeta is equal to old zeta. TRPO used K divergence to make new policy to be close to old policy. Instead, clip surrogate objective uses this L clip as a loss function, which encourages RT to be close to 1 so that new policy pi zeta gets close to old policy pi zeta old. Another proximal policy optimization algorithm is adaptive KL penalty coefficient. In TRPO, it was problematic that we don't know proper beta value here. This algorithm adaptively updates beta value according to the value of KL divergence. As we have a large beta value, KL penalty's influence on the loss function gets large. We are trying to maximize this loss, and loss gets large when KL is small. Therefore, large beta value leads to small KL and vice versa. Therefore, when KL gets too large, we will make beta value large and vice versa. We have a target KL divergence, the target, and compare current KL value with the target value to decide whether current KL value is large or small. These are the concrete conditions for KL being large or small, and update of the beta value according to their conditions.
Hi, I'm Sangok, and I'll continue to explain the evaluation part. The first evaluation is comparing several methodologies and searching the best hyperparameters. For the comparison, there is the baseline loss function with neither clipping nor penalty. And for the KL penalty, the author evaluated both fixed and adaptive penalty coefficients. The experiments used 7 simulated robotics tasks, which are simple examples of continuous controls. Policies are modeled as 2 fully connected layers for all tasks. The results are here, and they shows the clipping method its other methods. And we can find out the best hyperparameter for the clipping is 0.2. The adaptive KL penalty comes second, but is still better than the original fixed KL penalty methods. The next evaluation is comparison to pre-existing methods on reinforcement learning. The authors compared both traditional methods, including vanilla PG and CEM, and the state-of-the-art ones, such as TRPO and A2C. In the comparison, PPO is with the best settings in the previous evaluation, meaning the clipping with the coefficient 0.2. The experiment used same 7 tasks in the previous evaluation. The result shows PPO outperforms other methods on almost all the tasks. Also, it converges faster than any other methods. This paper was published in 2017, so many follow-up studies have been conducted. We found 3 variants of PPO. The first paper, POP3D, suggests a lower bound to the total variance of divergence. The second paper, TRG PPO, tweaked the clipping to be triggered on a twist reason. The last one, TPPO, improved the previous paper by modifying the clipping, able to roll back if necessary. Our project will start from replicating the implementation of this paper. The others publicly distribute their implementation in the web. We will re-implement all of 2 suggested methods and the simulation robotics task as the author did. And if any problem occurs, the author's original code can help our implementation. While there are some follow-up papers, we found that a simple variant of PPO was not tried. So we proposed mixing two PPO methods, the clipping and adaptive KL penalty coefficient. We want to test a linear combination of two loss functions can outperform the original PPO methods. Furthermore, we will willing to apply several algorithms used in machine learning, such as meta learning and adaptive method to determine the best gamma value. This is the end of our presentation. Thanks for listening.